Well, good morning, everyone. This seems like a good time to start, since I think most of the seats are now filled. Thank you all for coming. My name is Bruce Dawson, and I used to work for XNA Developer Connection, which is in the games industry, and I actually don't now. I hope nobody holds that against me. I'm not in the games industry, but this talk should still work. This is technology and techniques that go beyond just gaming applications. And, well, I hope you find this an interesting talk. So the basic agenda today, well, you can read it up on the slide, talk about locks, talk about lockless programming, blah, blah, blah. But really, my big goal here is to help game developers get a better intuition for the weird and unintuitive things that will happen when you try to do lockless programming. If you can reason about it, if you can get an accurate intuition, you're much more likely to be able to write correct code. And I also want to give some practical advice on, once you've got this intuition, once you know what the problems are, where they're going to occur, what do you do to write portable code that is going to avoid those problems? Everybody could remember to turn off their cell phones. I remembered to turn off mine, which is always a good thing for the speaker to do. That would be appreciated. On any talk that mentions multi-threading, and probably just on any talk these days, it's mandatory to mention something about the state of multi-core in the world. You already know this, but I have to mention it anyway. It's in the contract. There's a lot of hardware threads out there. 360, PS3, even $500 PCs have significant numbers of cores available. Now, you can always write single-threaded code, and these CPUs are generally really fast, so your code will run really fast, but you will be throwing away 75% or more of the power of this machine. So if you're trying to make the best possible, fastest possible game, unfortunately, multi-threading is unavoidable. Now, I like to say, hey, multi-threading is really easy, as long as you don't actually share any data. That's not going to work very well. So we're going to get into the tricky part of it pretty quickly. And I'm going to state right out, the best way to share data between multiple threads is to use locks. Yes, I know, this is a lockless programming talk, but I want to start by saying, are you sure you really want to be doing this? Because sometimes it's just not worth the pain, the bugs, and the complexity that comes along with it. Okay, with that out of the way. Here we have probably one of the most popular shared data structures in games these days, which is a job queue. One or more threads puts jobs on the queue, one or more threads pulls jobs off the queue, and work gets done in a multi-threaded way. And there's a few different parts to this. I'm using a standard SDL queue to actually store the different jobs. So nice and simple, doesn't require writing too much code. But the thing is, SDL queues are not and cannot be thread safe. So we have to add that thread safety at the appropriate level. So that's why, of course, we've got these critical sections here which ensure that one and only one thread can touch that job queue at a particular time. Now, this is not a fancy job queue. You could have work stealing in multiple queues and all sorts of other fancy things. But it demonstrates the idea of here's a simple job queue with locks. But, of course, there are some problems with locks. The one that I think most people start worrying about too early, in my opinion, is the overhead of locks. It takes a certain number of cycles to acquire a critical section and to release it. Honestly, it's not that big an overhead. It's been reduced over the years as developers have got better at creating fast critical sections. So don't assume that locks have too much overhead without measuring it. Deadlocks is a real problem with locks. If you're acquiring multiple locks, you don't acquire them in a consistent order, then two threads are both holding on to a lock that the other thread needs. Progress halts, your game locks up. That's a fatal problem. So that is a genuine problem. Contention is also a problem. It's critical section says only one thread can be in this piece of code at a time. So obviously, if there's a lot of threads trying to go in there, sometimes they're going to end up waiting for the other threads. And that can be significant. If you hold the locks for too long, let's say while doing a file I/O operation, then contention is going to be enormous. And there's a few things you can do to try to avoid these problems. Don't hold the locks for too long, but then you might need to acquire and release them too often. So we're kind of contradicting the first point. And if you have lots of little locks, then you're less likely to have contention, but now you're more likely to have deadlocks. So this is multi-threaded programming. It's messy. And the fourth problem that came to mind is priority inversions, where a low priority thread owns a lock, is unable to run for some reason, and a high priority thread needs the lock and is unable to run because it can't acquire it. And this actually happens far too frequently on the Xbox 360. The system thread is the ultimate high priority thread. If you've got a worker thread, it acquires a lock, the system thread comes along and steals its time slice, well, that worker thread goes to sleep for a millisecond while holding a lock, and progress may stop on other threads as well. So priority inversion definitely can be a performance cost when using locks. So the sensible thing to do is go, well, there's some problems with using locks, but hey, life is complicated. Let's just be careful in how we use them. Let's design things well, and life will be okay. Or you can go, screw it. Let's go lockless. That's more exciting. Okay. And with that lead in. So basically, lockless programming, it's techniques for being able to safely share data without ever acquiring a lock. Now, this may have low overhead. Don't count on it. Honestly, if you're switching to lockless to reduce the overhead, that's probably a bad reason most of the time. It does avoid deadlocks. You can't really have a deadlock if you're not acquiring a lock. And similarly, you can't have a priority inversion, or it's much harder to have a priority inversion if you're never actually holding a lock. If your thread gets swapped out and you're not holding a lock, then the rest of the system can continue running. But there's a lot of trade-offs for this. The sort of things you can do with lockless programming are very limited. Your fundamental operation is an interlocked compare and swap. So you can do anything that you can do with an interlocked compare and swap. And it turns out that's not everything. So there are inevitably going to be some trade-offs that you're going to run into and some additional complexity. It's hard to get this code right. It's hard to write it portably. You definitely don't want everybody on your team writing this type of code. So here's our job queue again. This is the one with locks, and we'll quickly get rid of the STL queue, and we'll replace it with a lockless data structure. And this is actually comes with Windows, comes with Xbox 360, so you can just start using this right away. So hey, turns out lockless programming is easy. And we don't need that critical section anymore because an S list, that data structure we're using, is a singly linked list, and there's magic functions that use compare and swap to update this list in a thread-safe way without ever requiring a lock. So 50 different threads popping and pushing items on the list, it will not get corrupted. And you're never actually acquiring a lock. So that's pretty cool. Well, turns out this, for most purposes, sucks, and you don't want to use it. And the basic reason is, if you watch the slide title very closely, you notice it changed from job queue to job stack. So an S list is singly linked. You're only pushing and popping from the front, so you don't have a queue anymore. So instead of being first in, first out, it's first in, last out, and most people want their jobs done in the order which they submitted them, and this does not guarantee that. You can still use it. It is a completely valid construct. It gets used in Windows and the internals of the kernel and a lot of different places, but it's certainly not a perfect scenario. It also, for reasons that I will get to later on, foreshadowing, all the best speakers do it. This is actually broken on Xbox 360 as it's currently written. So please don't copy-paste this into code that will ever run on Xbox 360. It's an easy fix, but we'll get to that. So it's all about the bounce. It's funnier with a bounce. Okay, so let's try a different version because we really want this to be a queue. And this is code you can actually write yourself and understand the techniques that are going on better than with the S-list, which is demonstrably weird on the internals. Basically, we have a circular buffer of presumably pointers, and we're going to put work items into that circular buffer. And we only have one thread inserting items. So that thread checks the read point and the write point to see, is there room? And if so, it writes a pointer in, and then after writing that pointer in, it increments the write point to indicate, hey, I've used that space. Cool. The worker thread, and you can only have one of these, there's always limitations with lockless programming, checks to see, is there any data in this circular list? It just compares the read point and the write point. If there is, it grabs a pointer from that work list, and then it increments the read point to say, hey, I've grabbed it, that space is now available. Does that kind of make sense? And the one that's assigning the work is the only thread that ever writes to write point. And the one that's pulling the work off is the only thread that ever writes to read point. So there's no concern that both threads will try and modify the same item at the same time. So this is lockless programming, and we don't even have any interlocked operations. And that's cool because those interlocked operations, those the atomic compare and swaps, are actually relatively expensive. So if we can avoid them completely, suddenly we've got code that scales really nicely, runs really fast. And indeed, as this code appears on the paper, it's correct. And if you were to get two people, one to play the thread assigning the jobs and the other one to play the thread receiving the jobs, and you were to do these steps at the instruction level, one at a time, interleaving arbitrarily, you would find that it always works on paper. But it's completely broken. Well, we'll fix it. Honest. Okay, so now I want to play around with establishing an intuition for why these things work or don't work, how CPUs work. And I've done my best animations ever. So here we have a simple CPU. It's too bad I can't see them, but oh well. We have a simple CPU here, and we've got instructions along the right, and I'm going to execute those instructions one at a time, and we can see this read happens. And the read goes from the CPU, which is an Xbox 360 CPU, in case you were wondering, goes from one of those three CPU cores down to the L2 cache and back. And it does that while the read instruction is executing, which is a really nice mental model. And then we do a write, and the write goes down to the L2, and then the instruction finishes, and we do another write, and it's much the same thing. It all just repeats. And the basic idea here is we ask to have an instruction executed, and it happens, and then it finishes, and then we do the next one. And when we're writing code, or when we're looking at assembly language, I think this is the mental model we have for how the machine works. Now, we know that it's more complicated than that. We know that there are out-of-order processors, and we know that there are caches, so that all these reads don't happen to the L2 cache. So we understand, certainly for performance reasons, that there's a lot more going on than this model would suggest. But I think that most of the time when we're thinking about the correctness of our code, this is roughly the mental model that most programmers have. And 20 years ago, with a 6502 or a 68000, it was reasonably accurate. But of course, now it doesn't reflect the reality, and some of the divergences are dangerous. So here's what actually happens. So in this animation, you can see a bunch of different things. First of all, we've got the instructions executing along the right, and they actually all finish executing before the writes make it to the L2 cache. So that's pretty normal and expected. It takes a long time for a write to make it to shared storage, even if it's just the L2 cache. The instructions keep going regardless. The other thing to note, and I'll just run it again, is that for some reason, the write to PB got delayed. It just spun around in a circle. They don't actually spin around in circles, to my knowledge. But there are store buffers. There are weird things going on. And I thought about trying to emulate something slightly more realistic, but a combination of it not mattering and PowerPoint not wanting me to said, this is good. The basic idea is they don't necessarily make it to shared storage in order on some processors. So we've got the order that you can see the instructions in the code, and then there's the order that the writes actually make it to the L2 cache. And when people talk about reads and writes being reordered, that's what they're talking about. When do they become visible to other people? It's sort of a philosophical question. And in this philosophical question, I don't care when the instruction started executing. I don't care when the instruction itself finished executing. I only care when did the data go to or come from the L2 cache. That's when that write became visible. And for purposes of reordering, what was the order? That's what matters. So in this case, we executed writes to A, B, and then C, and they were visible in the order A, C, and then B. So that's what the L2 cache saw. That's what other processors would see. That's going to be confusing. Roughly the same thing happens with reads. Here we're reading from A1, then A2, and then we read from A1 again, and it gets satisfied from the L1 cache. So what does that mean? I mean, I was saying that what matters for reads and writes in terms of their ordering is when they go to or come from shared storage. So that second read, when did it come from shared storage? Well, it's getting the value that the previous read grabbed, or a prefetch, or something else. For some reason, that data was in the cache. So its time, if you were to write down the time that the data came from L2, is whenever that data that went to L1 got loaded. So it's reading data from the past. It's like a time machine. So the effective order of these reads is A1, A1, and then A2. So if somebody was constantly modifying data in the L2 cache, writing new values every cycle, then the two reads of A1 are going to show the same value, even though in the code they shouldn't. This one is even harder to think about, but kind of weird. And I can't come up with an explanation for when or why this would happen, but hey, CPU designers are crazy. So we can only assume that reads can, in fact, pass writes. And when you're talking about when did this read happen, when did this write happen, it's when did the data come from L2 for the read, and when did this data go to L2 for the write. So the visible order reversed, as usual. Okay, and this one is probably the weirdest and most complicated and nastiest. So we read from A1, and then we do a write, and then we read from that location that we just wrote to. So what happens? A lot of things are happening. When we read from A2, the processor wants to make sure that your single-threaded code is correct, because otherwise we'd be storming Intel with pitchforks and there would not be any happiness. So if you write a value and then read back that same value, you'll get the value you wrote, even if it hasn't made it to L2 yet. So you've written a value, you're reading it back, you are now seeing values in that memory location that no other processor can see yet. So that's a kind of weird bit of time travel. So that's one thing that's going on. Let me run this again. The other thing is A1 is coming out of the L1 cache, because on the second read of A1, it's coming out of the L1 cache. So it has effectively been moved forward in time quite a bit. So the effective order is read A1 for the second time, write A2, and then read A2. So that read has been moved ahead of the write. And that can be very important in some circumstances. So we'll talk about that a bit more later. But here's kind of the summary, the not complete but close enough for almost all purposes summary of the memory models that game developers care about the most. So there's 4 different types of reordering. Can loads pass loads? Can stores pass stores? And stores pass loads and loads pass stores. And the rule for PowerPC is very simple. It's just yes. And when I say pass, I mean, let's say you do a store and then you do a second store. If the second store moves ahead of the first one and gets to L2 first, then it has passed it. So when we're talking about passing, we're talking about the later instruction passing the earlier one. When you're talking about writes versus writes, it doesn't matter which one is doing the passing. But when you're talking about a load passing a store, it becomes critical to know, well, which direction are we passing? And it means that that later instruction, that second one, is passing the earlier store. So x86 only does one of these types of reordering, so that is some comfort to Windows developers. x86 and x64 are the same, and this is actually now documented for about the first half of the multi-core revolution. You had to know somebody who knew somebody to know for sure what the memory model was, but it is actually documented now. And there's additional complexities about total ordering on a memory location and things like that, which can become complicated if you're really pushing things hard. But for most purposes, this is all we need to care about, are these 4 different types of reordering. So an obvious question is, PowerPC is obviously of the opinion that we should do everything possible to make the processor run fast, no matter how complicated it makes life for developers. So we'll reorder everything if it gives us a tiny advantage. And Intel and AMD are clearly of the mind that, well, we shouldn't do this reordering because this is going to mess with people's heads too much. Let's try and avoid it. And yet they still left in one type of reordering. So why? And I think another animation will help demonstrate it. So here we're doing a read, a write, and then a read. So this is showing, well, what happened if we had some mythical CPU where reads could not pass writes? So that last read, we're going to say it can't pass that write. Let's see how slowly this code executes. So we do the read, we do the write. We could then do the other read from the L1 cache, but we're not allowed to do that. We have to wait for that store to finish, which basically means that that second read, even though the value is in the cache, nice and close to the processor, has to follow the write all the way down to the L2 cache and come back up. It would absolutely kill performance. So reads must not pass writes on any sensible high-speed CPU design is really what that means. So reads passing writes is a necessary thing in order to get good performance on a high-speed CPU. Otherwise, you're basically disabling the L1 cache in a large number of scenarios, which is really not a good idea. So you're always going to have to deal with the possibility of reads passing writes. And we'll come back to this one special case a bit later as well. It does show up in multiple places. So let's show what this actually means to your code. And this is sort of a simplified version of that lockless queue where it was a single reader, single writer. And that's a generic form of publisher-subscriber. One thread publishes some data, makes it available for the world, and another thread notices that it has been published, and they read from it. They're subscribing to it. And this is being done in a lockless way, and only works with one writer and one reader. Basically, you write the data to memory, and then you write a flag saying, yo, the data is ready. And then the reader checks that flag, and if that flag is true, then it reads the data. And is this safe? And as with the lockless queue, this code is safe on paper, but broken as executed. So let's just see what happens. So processor 1 writes the data, then writes the flag. Processor 2 reads the flag, then reads the data. So processor 1 does the 2 writes, and if they get reordered, what happened there was that the flag actually got reordered, so it got written first. We'll just run that again, because I spent a lot of time making this. For mysterious reasons, it's not ours to worry about why, but for mysterious reasons, the write of the data got delayed. And this can happen on PowerPC. So now, because the writes have gotten there to the L2 cache, to the shared storage, in this case L2, out of order, another processor might see that the flag is set and the data is not there, so they go to read it and they get garbage, which would be bad. So we fix this. Now we're getting into the solutions. It's not all problems, people. We put in what's called an export barrier, or it's got various names. I'm calling it my export barrier. Very creative. So the basic idea is we do that write, and then we execute an export barrier instruction. And an export barrier is a no passing sign. That's all it is. It's not allowed to pass writes that are ahead of it, and writes are not allowed to pass it. That's a simple rule. And yet that's sufficient, because all we need to do is make sure that the data gets there before the flag. And as long as they don't pass each other, or as long as they don't pass this barrier which is between them, then your code is fixed, at least on this side. And the nice thing about these is they don't necessarily need to slow your code down significantly. The writes can still head straight down to L2. There's not a lot of waiting around. It's just not passing other writes, which is, they're both going the same direction. It's just somebody driving in the left lane and stubbornly refusing to pull over so you can pass. You're still going to get to your destination. It's going to be okay. Just chill. But reads can also be reordered. And this is the general rule of lockless programming. Reordering is going to happen when you're writing the data, and it's going to happen when you're reading it. Handle both cases. Look for symmetry, because symmetry is beautiful and more likely to be correct. So here's roughly what can happen on the reader. So we start out with the writer doing the same thing, does the write, does the memory barrier, does the write of the flag. Life's good. Then we go in, we read the flag, and it's set. And that's all well and good. And then we go and read the data, and it comes from the L1 cache. Oops. Because that data in the L1 cache was stale. And this sort of reordering can happen. We've basically, because of the L1 cache, or because of other purposes, there are other reasons why those two writes might have been reordered. Speculative reads happen even on in-order processors. There are lots of reasons why those reads might have been reordered. The net effect is the same. You read the flag, it says the data is good, but you've got stale data. So, no good. So, and there's eventually, I meant to make this point, when you write data to the L2 cache and some other processor has it in their cache, the processor doesn't leave stale data there indefinitely. At some point, the L2 cache will send a little message up there, either saying, here's the new data, or throw away the old data, it's no good anymore. So obsolete data will not sit around forever. It will not sit around for very long. But you can't tell your producer, this won't crash very often because the invalidates will usually make it work. When one processor writes, there is a delay before other processors see it, and you don't know how long that delay is going to be. The only sensible thing you can say is, if I see this flag set, can I guarantee that I will see the data that it controls as well? That's the guarantee you want. And for that, you need the export barrier and the import barrier. It would be nice if we could have the data show up instantly, but until somebody revokes the speed limit on light, that's not going to happen. So the solution is we need an import barrier. And I don't know how accurate my ruminations on how these things work are, but it doesn't matter too much. So we start out with the writes, and again we have the barrier to stop them from going out of order. And then we go and read the flag, and we see, oh look, the flag is set. And then we execute this import barrier instruction, and you have to hit another button for that. It goes down, and basically what it's doing is it's delaying or heading towards the L2 cache or doing whatever the CPU designers know is necessary to make sure that you've waited long enough. And that might be as simple as wait 4 cycles and then the invalidate's guaranteed to have showed up. Or it might be something more complex. I don't know. But it's guaranteed to work like that no passing sign between the reads. It does not let the older read past the newer one. And I've suggested this a few times, but I want to make this completely explicit. I don't care about reordering of instructions. When desktop CPUs reorder instructions and make them run faster, I'm very happy. And the fact that those CPUs tend to not reorder memory accesses is amusing and kind of nice. And then the in-order CPUs on the Xbox 360 and presumably the PS3 don't reorder their instructions, but they do reorder their reads and writes. So don't confuse the two. Reordering of instructions is always hidden to the programmer. That's good magic. Reordering of the reads and writes and when they reach shared storage is not always hidden and is sometimes bad magic. So don't confuse the two. So you might look at this and go, wow, those reads being reordered are really a pain, and those writes being reordered are really a pain. So, dude, x86 for the win, right? We'll just drop those consoles and we'll never have to worry about this again. So, turns out that's not the case, and you have to worry about these problems just as much on the PC for slightly different reasons. And that's because CPU designers are evil and will rearrange your code even if it changes its meaning, and compiler writers are evil and will rearrange your code even if it slightly changes its meaning. And in both cases, their rules are they will not rearrange your code if it changes the meaning of single-threaded code, but they don't acknowledge the existence of multi-threading. Compilers in particular, they don't know which variables are shared, so they will rearrange them like crazy. So you have to rein in your compiler just as much as your CPU. And just as we used barrier instructions to slow down the compiler, or to stop the CPU from doing bad things, we use barrier intrinsics to rein in the compiler. So I had the my export barrier define used to solve that publisher-subscriber model code. And it turns out we can use that same thing, just with different definitions, to solve this problem for compilers as well. On the compiler, on Visual C++ at least, you can use an intrinsic called read-write barrier, which stops reads and writes from moving past it. It's just a no-passing sign. So if you define my export barrier as read-write barrier, then you're fixing your code. On PowerPC, LWSync is the recommended instruction for preventing this reordering. So on that platform, we just define my export barrier as LWSync. And LWSync also prevents the compiler from reordering. So it's doing both at the same time. If somebody says to you, hey, I wrote this lockless algorithm and I know it's safe because I put in barriers, don't start feeling really happy about that. It really matters where you put them. So in this case, we're writing data and then a flag, and we need to make sure those are not reordered. The barrier has to go between the write of the data and the write of the flag. Otherwise, it's useless. So the standard method is write the data, export barrier, write the flag. And that export barrier and flag write is known as a write release. You'll sometimes see that in documentation talking about these concepts. And then we have the import barrier case, which is very similar. I'm still going to use read-write barrier for the compiler intrinsic on the PC. Technically, I could probably have used a write barrier for the export barrier and a read barrier for the import barrier. And if you want to micro-optimize your code, you could try doing that. But I really wouldn't recommend it because these things are so subtle. It's so easy to miss some subtle difference in what that's going to mean. And the change in performance is likely to be extremely negligible. So I just go, read-write barrier, go, good. It's just a compiler intrinsic. It's not going to affect performance. I'm going to go for the safer one. And it turns out on Xbox 360, the recommended import barrier instruction is LWSync. Same one, same for export and for import. On other platforms, they recommend iSync. They're both guaranteed to work, but we were told that LWSync was a better choice on Xbox 360. So, hey, fine. Once again, positioning is crucial. And if you read a flag followed by an import barrier, that's known as read-acquire semantics. It's worth mentioning that this definition of export barrier and import barrier really does give you exactly the same semantics on both platforms, PowerPC and the Windows platform. To the extent that the LWSync actually doesn't stop reads from passing writes, because that's a very expensive barrier to put in. So LWSync, it's lightweight sync. It does not prevent that one most expensive to stop type of reordering. And on the PC, the CPU could still be doing that type of reordering. So you put those barriers in, you're not stopping all reordering. You're stopping the first three kinds. The fourth kind is still potentially going to happen, but for the publisher-subscriber model, you're done. It's sufficient. So here's our fixed job queue. We added an export barrier and an import barrier. And this was roughly what my slides looked like until Monday. And I was thinking, this doesn't feel right. It feels like as control of the data is passed back and forth, there should be an export and an import on each of the threads, not just one on one thread and the other on the other. So I thought about that for a while and talked to some people. And the conclusion we came to is that you actually do need an export barrier here as well for kind of subtle reasons. When we update the read point, we are basically freeing memory. We're incrementing that pointer and saying, okay, that data that read point used to be indicating has been read from, we're done with it, you can use it. It's considered bad form to use memory after you've freed it. And if the compiler or the CPU was to move that write to the read point up above the read from the circular work list, then we've potentially got a problem. We've got a window of opportunity where we could get corruption. That pointer that we're going to read could get overwritten before we actually read it. So I'm positive that that one is needed. There's also one up here which, at least for symmetry purposes, is obviously needed. We've read some flags, and then we're going to write some data to it. It's harder to imagine a case where that would actually be broken because of the flow control in there. We can't write to that item until we've checked those flags. So I suspect that that one is not necessary unless you really like the symmetry of it. On the alpha processors, which are famous for being pathological about reordering beyond everybody else, it was probably necessary, but nobody cares about alpha. So at least 3 barriers needed in here, and the 4th barrier or a comment saying, I'm deciding to go for it. So, hey, correct code. It's only taken 38 minutes and 30 slides to get some code that's not broken. Okay, well, we got a few other examples, getting slightly more esoteric, but still potentially of interest and things that you need to know about. This is called Dekkers-Peterson's algorithm. I'm not showing the entire algorithm. This is basically a technique for doing mutual exclusion without using a critical section. Generally, you should just use a critical section. This only works for 2 threads. It's pretty subtle. But sometimes, say when writing kernel code or interrupt code, you might actually need to write something like this. And the basic idea is both threads set a flag, and then they check the other thread's flag to see if that other thread is trying to get in as well. And if they see that the other thread's flag is set, then they've got to fight for it, and those are the details that are omitted. But the initial idea is set a flag, check the other flag, see if we're in. Here's a little animation on our trusty Xbox 360. And the 2 CPUs do the writes. What a coincidence, they both did the writes at exactly the same time. They wrote their flag values to L2, and then after that, they both did a read from the other thread's flag. And if we go back and run that again, we can see that the reads were satisfied from the L1 cache. So for some reason, those flag values were in the cache. It's actually not too improbable. So effectively, they read stale data. They read data from the past. Those reads were reordered past the writes. And this is the one type of reordering, reads passing writes, that can happen even on x86 and x64. So this code is broken on every computer. Oh yeah, and eventually there will be some invalidates. The L2 cache will say, oh, those flags there, oh, too late. Sorry. So, epic fail. Doesn't work anywhere. So we need a memory barrier here. But the normal memory barrier that we use with the read-write barrier intrinsic on Windows and the LW sync on PowerPC does not stop this type of reordering. This is the one type. It does not stop because it's usually too darned expensive. But this time we need to stop it. We need to make sure those writes are not reordered. So we need a different type of barrier, and we'll call it memory barrier. So now the writes go down. They take their sweet time getting down there. The memory barrier instructions execute, and they have to go all the way down to the L2 wait and make sure that everything's cleaned up, make sure the invalidates have time to go back, and only when they've gotten back to the CPU core can those reads proceed. And that guarantees they're not going to be reordered. And you can see just by the length of the animation that this is a more expensive instruction. On PowerPC, it's called sync or heavyweight sync, as opposed to LW sync or lightweight sync. So they try and make it really clear that this is more expensive, but when you need it, you got to use it. So this memory barrier is needed on all CPUs. And it turns out, this macro you don't have to invent yourself. That particular macro name was chosen because it already exists on all platforms that Windows runs on and on Xbox 360. So I've listed the definitions there just for, I don't know, educational purposes or something. But you can just use this anytime you actually need a full memory barrier and implement it on, whatever other platforms people might make games for, and you'll be all set. If you're working on a single core system, you don't need to worry about this stuff. So this is the fixed version of Dekkers-Peterson. So that's the most extreme type of reordering you're trying to get. And my conclusion after researching this and writing up these slides and working on this for a while is that these three types of memory barriers, the import barrier, export barrier, and full barrier, with cross-platform definitions, much like the ones that I'm showing in these slides, are really the best solution, the necessary solution for making this stuff work. But some people are going to wonder, well, what about volatile? Can't I use volatile and then my code will magically be thread safe? And the answer is kind of a no, yes, no, and it's really confusing, which is a bad start. So standard volatile semantics, no. Simple answer, they don't work. And there's a few reasons. One of them is that volatile just says, well, you can't omit the read, you can't omit the write, and you can't reorder volatile reads and writes relative to each other. But hey, any other reads and writes, you can reorder them around as much as you want. So probably the only way you'll get what you want is to mark all of your variables as volatile. Bad idea. And even then, it does nothing whatsoever to prevent CPU reordering. So it might be adequate on x86 and x64 because they don't do much reordering, but that's not really a good solution if it only works on one platform. So that's the standard volatile semantics, which I assume is what GCC and compilers like that are using. Visual C++ 2005 saw this as a problem and thought that improving volatile was the solution. They're not so sure whether it was the right decision now, but it was an experiment. So Visual C++ 2005 and beyond, volatile reads actually have read-acquire semantics, meaning they will prevent all other reads from going past them in the way needed for a read-acquire. And all volatile writes have write-release semantics. And this includes, if you use volatile and you compile your code for Itanium, I don't have an Itanium machine, but it's fascinating to compile code for it and look at the assembly language. I am such a geek. You can actually see that Visual C++ 2005 and beyond will put in memory barriers on Itanium read and write instructions to volatile variables. So cool. If we just mark our flag variables as volatile and always compile our code with Visual C++ 2005 or better and just forget all those other platforms, then we're set. Except that on Xbox 360, we didn't put in the memory barriers. So I told you it was messy. So it doesn't prevent hardware reordering on Xbox 360 because of the lack of memory barriers. It's hard to recognize something that is that complicated. The only reason for using volatile would be to make your life simpler, and it utterly fails to do that. Atomic of T is the C++ OX feature, which is what people think volatile is. And it goes beyond that. So that will actually be a cross-platform portable way of writing this sort of code sensibly. And you can specify what type of barriers you want every time you read or write from these variables. So that is going to definitely simplify life. But we don't have it yet. I wanted to give one more example, a case where people often can hit problems with this. And this is a technique called double-checked locking. And we can think of this as being the final exam for this lecture. Scott Myers wrote a paper on double-checked locking and how it was broken. So if you've read that, you have an advantage, and that's fine. The basic idea of double-checked locking is we're creating a singleton. We want to make sure it's only created once. We don't want to have to acquire a lock and release the lock every time we go in to grab a pointer to that singleton, but we need to be thread safe so that only one thread tries to actually create it. So how do we do that? And double-check locking is the idea of we'll check the pointer. If it's non-null, then we're done, and we're really fast, and that's what we want. If it's null, then we'll acquire a lock, check again to see whether it's null or not, and then create the object. If it is null, assign it, release the lock. So this is all great, but as you would probably expect, there are some reordering problems here. Despite the fact that locks, and I should have mentioned this earlier, locks are full barriers. That's why locked programming is simple, because all this stuff about reads and writes passing and moving, reads and writes never pass a lock acquire or a lock release. That's one of the things that makes that world much saner. So despite the fact that we've got the lock acquire and release here, this code is broken and needs some memory barriers. Anybody want to yell out where a memory barrier would be a good idea? First line where? There's two ifs. If not temp. That would not be before if not temp. Yes. Yes. Woohoo! You're not just randomly choosing places, are you? Because there's not that many lines. And what type of barrier do you need? Import or export? Da, 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 da. Yes. Okay. Wow, he's lucky. Okay, and there's another one. That's the one I didn't think people would get. Go figure. Okay, so here are the barriers that are actually needed. So I'm going to look at the export barrier first. The problem is you're constructing this object, which means you're writing to its fields, and then you are taking a pointer to that object and writing it to a global variable. So you are publishing that variable. And you'd better make sure that you don't publish the existence of that new type, the new object, before it's actually constructed. So if that write to the pointer were to get moved up, and compilers can do this, or the CPU can do this, above part or all of the construction of the object, then another thread could potentially see this partially constructed or not at all constructed object. And then the import barrier it's kind of an annoying one because you end up having to execute it every time you call this function, and yet it only really is necessary in the first few hundred cycles after the object was created. But potentially somebody could read that pointer and then go and read the contents of the object and read stale data from there because read reordering. So you need that import barrier and that export barrier in order for this code to be correct. The export barrier, not a big problem. It's only executed once. The import barrier, well, probably fairly cheap. And hey, having your code correct is kind of important. So anyway, there's an excellent article from Scott Myers talking about this. Interlocked exchange, interlocked increment, and things like that are also an important part of lockless programming. I mostly steered away from them. They are critical. Sometimes you need to do an interlocked operation. Interlocked increment for reference counts is an obvious example. But they are unfortunately made a bit confusing by their non-standard behavior on Xbox 360. The goal for these functions was that they're all supposed to be full memory barriers. And on Xbox 360, they are not. So therefore, your life becomes more complicated. Almost every time you use these, you need to remember to add a barrier, because you're almost always using them to acquire or release access to an object. So what we did, and this is portable to Titanium and Windows and Xbox 360, is they're the acquire and release versions of most of the functions. And if you use those when you want to acquire access or when you want to release access to an object, they contain the necessary memory barrier. It's not as expensive as a full memory barrier, and it's much easier than using interlocked whatever and then manually putting in the barrier. So absolutely recommend it. If your code ever needs to run on Xbox 360, I'll just say you should never use a raw interlocked anything. It should always be interlock something acquire or interlock something release. So, lockless programming, it's definitely limited. If you try and create a queue, it'll probably actually be a list or only have a single reader or a single writer. There's lots of complications and some potential bugs, but sometimes it is going to be the right solution, especially for games with our unique performance needs. So this is a list of some of the things that I think are common and reasonable uses for lockless programming. Using S-lists or XM Core on Xbox 360 means you can get some more subtle algorithms that have been written and tested by somebody else, so that can be a good option as well. These are the three barriers that I think you need that should cover most of your lockless programming needs. And the thing to think about is figure out when you're publishing data and when you're subscribing to data, because you're almost always doing one of those two things. And then use the appropriate barrier in the right place, and your odds of being correct will have gone up slightly. So in summary, don't do lockless programming. I know it's kind of a silly summary, but the slightly more subtle summary is there. Do profile your code. Don't just assume that locks have too big a cost. Make sure they're actually a problem, because, as always, it's more important to get your code right than to have it run that infinitesimally little bit faster. And there have definitely been cases where people have converted code with locks to lockless, and it's run slower. I will be making these slides available, presumably on the GDC website and probably on the Microsoft website where we put all our presentations on the XNA website. So take a look for it there. I've got some references here, which are the Intel and AMD documentation of their memory model, which are actually reasonably well written. And then a PowerPC article which discusses the PowerPC memory model and is the best explanation that I've ever seen of it. A white paper that I wrote. And then Scott Meyer's talk or presentation on double-check locking, which is also quite excellent. And I think we have 5 minutes for questions. Oh, yes, certainly. Yes? Is thread memory barrier in Game Studio? I would guess that would be a full memory barrier, but I have not actually used it. But I'd be about 99% certain that it is. Yes? So how much more expensive is a full memory barrier than the lightweight memory barrier? I haven't actually measured it. When I left the XNA group, they took my dev kit. On Windows, it's certainly going to be more expensive because the import-export barriers are just compiler intrinsics. They potentially have a cost of 0. I think it's going to be on the order of 100 cycles or so more. So it's not something you want to do in an inner loop, but when you're worried about making your code correct, then it's a no-brainer to put that in. So I'm going to guess 100 to 200 cycles for a full barrier. Yes? What is a reasonable way to find these problems? I mean, writing stress tests that intentionally use your job queue in pathological ways is one good thing. I know Microsoft Research is working on some techniques for automatically detecting the potential for these things. And it's a research project. They don't have a really good solution. So I'm afraid I don't have anything really helpful to offer you there. Yes, last question.
So one of the problems with lockless programming is that you're using a thread programming paradigm that requires serializability.
Right.
That you want to be able to map these down to a single processor context. But that's not the only way to use threads. You can also do data parallel. And there are a lot of applications in games, particularly in simulation loops,
Right.
for doing data parallelism, though it requires different programming style.
So basically saying data parallelism avoids most of these problems, or at least postpones them substantially. And I would say I totally agree, and the best way to make your life simple is don't share data so frequently that this ever becomes a problem. And data parallelism is one way. Having two threads which are working on completely different tasks so that they don't need to share data very frequently. There are a lot of ways of, hey, if sharing data is the problem, let's make sure we're not doing it too frequently. And if we're not doing it too frequently, maybe we can just acquire a lock, copy the data, and release the lock, and our life will be much simpler. So yeah, totally valid ways of dealing with this. Yeah? None of these should ever happen in a single-threaded application. I should have made that completely clear. The compiler will only rearrange your code in ways that will not affect single-threaded code. That's its job. If it breaks that, then your compiler is broken. The CPU will only arrange your instructions in a way that will not break single-threaded code. So it's only when you are writing multi-threaded code, potentially on a single-core system you could have this, but you need to be writing multi-threaded code before any of these problems will hit you. So that is the other solution. Let's just all give up on multi-threading. All right, thank you very much for attending the talk. Please fill the feedback forms.